Welcome back, y'all. In this video, we continue our conversation about general linear systems problems. Remember, in a general linear systems problem, we have an m by n matrix and a right-hand side vector b, both arising from a given context, a modeling context. We're searching for the vector x, which is n by 1. We've now seen in multiple videos that the complete solutions x to these general linear systems problems will take the form p plus z, where p is a particular solution and z is a trivial solution to the corresponding homogeneous linear system problem. We're going to use the opportunity in this video to really iron out what those zero solutions, what the solutions to the homogeneous linear system problem should look like. When we have a rectangular matrix that has m rows and n columns, we say that the number of linearly independent solutions to the ax equals 0 problem is going to be equal to f, the number of non-pivot columns in our matrix. In order to define the number f, we say it's the number of columns minus the number of pivot columns. N is the number of columns in our matrix. We define the scalar r, which we're going to call rank in a different video, as the number of pivot columns in our matrix. And then anytime we're looking for special trivial solutions to the ax equals 0 problem, we expect f number of those, each of which is linearly independent. We've now seen in both of the toy problems that we've worked with a mechanism for generating these, and we also saw a proof that those vectors that we created were linearly independent. We're now in a position to recapitulate all of these observations in a formal theory that gives a more specific general template for complete solutions to general linear systems problems. We're going to call this the superposition principle for solutions to a times x equals 0 problem. If we start with a m by n matrix A, and we say that there are a total of f non-pivot columns in that matrix, we'll say that the z1, z2, all the way to zf vectors, each of those has n columns. We'll say those are the special linearly independent solutions to the homogeneous linear system a times x equals 0. In other words, when I multiply the matrix A by any of those z sub I vectors on the left, that matrix vector product will always get 0 by the construction of those vectors. In this situation, we say that any solution to the a times x equals 0 problem can be written as a linear combination of the special trivial solutions where the z sub I vectors come into play. In other words, that general vector z, where we said x equals p plus z, z actually is written as c1 times z1 plus c2 times z2 plus ... plus cf times zf for any constant values c1, c2, all the way down to cf. That superposition principle actually implies that we can substitute that z in the general template for our complete solution for this linear combination of special trivial solutions. And if I want to find the exact solution template for a specific problem, I should really be searching for those special trivial solutions in each case, which is exactly why RREF form is such a powerful mechanism to help me solve general linear systems problems. Now that we have our solution template in hand, along with the superposition theorem for what these trivial solutions to the homogeneous linear system should look like, let's go back and analyze the 3 general linear systems problems that we've solved and elicit these forms from those systems. The first general linear systems problems that we analyzed was what I called the final approach, GLSP. That was the one having to do with the cubic polynomial path of a plane coming down to landing. We started that problem with a 4x4 matrix and a 4x1 vector, and then used elementary matrix operation on the left-hand side to transform this matrix vector product into this special form in upper triangular structure with non-zeros on the diagonal. Once we had our system in special form, we counted 1, 2, 3, 4 pivot columns, and then we used the backward substitution algorithm to solve our problem and produce this solution. Now, we did not show that actually this solution was a particular plus a trivial. Because we have 4 pivot columns and a total of 4 columns, we know that the number of non-pivots in this example is 0. In other words, we have no linearly independent solutions to the corresponding homogeneous linear system problem. The only solution that we have to the homogeneous linear system problem is the trivial one. In other words, only one vector gets sent to 0 by our original matrix, which is the 0 vector, 0, 0, 0, 0. And yet still, we see this general solution template for the complete solution holds, particular plus something that gets sent to 0. In this case, the thing that gets sent to 0 is the 0 vector, and that's why this non-singular linear system problem seems to have only one solution, and we don't generally write it with that particular plus trivial solution. With a recap, we saw that in the final approach GLSP, we started with a 4x4 matrix. Every column of that matrix was a pivot column, so the rank of the matrix was 4. We had a total of 4 columns, which means that we have 0 non-pivot columns, because 4 plus 0 is indeed 4. When solving the original linear systems problem, we wanted to find complete solutions in the form particular solution plus trivial solutions. The trivial solutions are going to be linear combination of the special trivial solutions, but there are no special trivial solutions. The only thing that gets sent to 0 is the 0 vector itself, which means that the general solution is just the particular solution. This is why we say that non-singular linear systems have unique solutions. The only solution that's sent there is the particular. There's no extra information stored in non-pivot columns. The last thing that I'll note is the 0 vector is always linearly dependent, and that goes back to the definition of linear dependence. Moving on to our first toy example of a general linear systems problem, we saw that we started with this integer matrix and an integer valued right-hand side vector. The point of this example was just to illustrate the template for the solution. Once we had this AX equal B problem with 3 rows and 5 columns, we used multiplication on the left by a sequence of elementary matrices to transform this into special form UX equal to Y. And with that special form RREF matrix, we saw that there were a total of 2 pivot columns. There's a total of 5 columns in that matrix. There must be 3 non-pivot columns, 1, 2, 3. Using our knowledge of the general template for complete solutions to the system, we leveraged the structure of our RREF matrix to find our particular solution plus a general trivial solution, which was a linear combination of the special trivial solutions. Each special trivial solution gives the user, us, a representation of the linear dependence relationships between each non-pivot column and previous pivot columns. So Z1 in this situation told me if I multiplied 2 times column 1 plus 1 times column 2, I would get to 0, which means column 2 comes from multiplying column 1 by a -2 value. Z2 in this situation tells me that 1 times column 1, 0 times column 2, -2 times column 3, is equal to -1 times column 4. Or in other words, if I take 1, -2, 1, that linear combination of the columns goes to 0. These two are linearly independent because the 1 value in that position is the only 1 value in the entire set of special trivial solutions. And the same thing is true for my second z. That 1 value in the 4th row, that is the only non-zero value in the entire set of special trivial solutions. These indeed are linearly independent. And thus, when I want to find the general template, it will take the form particular solution plus linear combination of my linearly independent special trivial solutions. The last thing that I like to push my students to do is to recognize that that linear combination can be written as a matrix vector product. The number of columns of that matrix aligns with the number of non-pivot columns of my original matrix, and then the number of scalar coefficients has the same size, which means my general template is a particular plus a linear combination of special non-trivial solutions. That's exactly what our theorem tells us we should expect. For good form, let me show you exactly what that large matrix Z looks like. Here's my particular solution. I can group this linear combination as a matrix where the columns of that matrix come from the individual columns of my linear combination times a vector. The scalar entries of that vector are the scalar coefficients in front of each vector in my linear combination. That is yet a different way to map that same general template for solutions to AX equals 0. Finally, the last example that we analyzed, our second toy example, had a 4x7 coefficient matrix, a 4x1 right-hand side vector. All the entries were integer coefficients because this was not a modeling problem. This was a let's use simple math to illustrate an idea problem. Once we had this system, we multiplied on the left by a sequence of elementary matrices, transformed it into the equivalent special form ux equal y. And in this special form, we saw that there were 1, 2, 3 pivot columns, total of 7 columns. 7 minus 3 must be f equal to 4, 1, 2, 3, 4 non-pivot columns. We used our knowledge of the linear dependence relationships between the non-pivot columns and previous pivot columns to generate 4 linearly dependent solutions to the AX equals 0 problem. We also wrote the right-hand side vector y as linear combinations of the pivot columns uniquely, which is exactly how we got our particular solution. This led us to the complete general solution. X is a particular solution plus a linear combination of special trivial solutions, which are linearly independent. In our video on this, we actually proved that those are linearly independent. But this structure for this solution follows the exact pattern that we want, a particular solution plus a trivial solution. We now have a theorem in our pocket that says any trivial solution to the homogeneous linear system can be uniquely written as a linear combination of the F special trivial solutions, each one corresponding to a single non-pivot column. And thus, because there are 4 non-pivot columns, we expect 4 vectors. When I coach my students to do this, I like to say not only can we write it as a linear combination, but we can also write it as a matrix vector product. The F columns of that capital Z matrix are just going to be the individual special trivial solutions. And then we're going to collect the corresponding coefficients in a vector of the same size. That means that we can translate the template for the complete solution into vector plus matrix times vector, P plus Z. In each of those 3 examples, we see that the complete solution, that template that we had, particular plus 0 solutions, came into play. Moreover, this theorem about superposition, the theorem that says any 0 solution is going to be written as a linear combination of the F number of special trivial solutions. Any 0 solution is C1 times Z1 plus C2 times Z2 plus ... plus CF times ZF, where F is the number of non-pivot columns. These two things combined allow us to solve with great precision any general linear systems problem that has a solution. Now that we have this theory under our belt, we're going to refine our approach by introducing some formal technology and terminology that will allow us to precisely refer to all of the pieces that are in play when we go to solve these problems. That's exactly what we're going to do in the next video.